Hello everyone, welcome to lecture 5. Today we're going to talk about chapter 7.5 on the textbook, relative extrema of a function of two variables. First, as usual, before we talk about anything, we need to give a proper definition. Now, what is the definition of a relative extremum? Well, first let's define relative maximum, and the relative minimum is defined in a similar fashion. Here is the definition. Suppose f is defined a function f as a variable of x and y, say, is defined on region containing some point x naught, y naught. Then x naught, this point x naught, y naught, is a relative maximum if there exists a circular region R centered at the point x naught, y naught, such that f of xy is smaller than or equal to f of x naught, y naught for all xy in region R. Okay, this is the proper definition for a relative maximum. Now, what does that mean? So suppose this is the point x naught, y naught. Then we find a circular region. It can be a very small circular region. It doesn't have to be a big region. As long as you can find a small enough region such that, for example, let's take this tiny little region around that point, such that in this region, the value of f is smaller than or equal to the value of f evaluated at this point. Then this is a relative maximum. So it tells you it's a local property. A function can have multiple relative maximums. For example, in this graph, these 2 points are both relative maximums. The value of f here, well, in this case it's z, the value of z here may be larger than the value of z here, but it doesn't matter because we only care about the ability to find a very small region around the point such that the value here becomes a maximum. Okay, so these 2 points are relative maximums. Similarly, that's not how you spell similarly. this point x naught, y naught is a relative minimum if f of xy is larger than or equal to f of x naught, y naught for all xy. Okay, so we have a definition for relative maximum and a definition for relative minimum. All right, notice that here it is a non-strict unstrict inequality. So it's just larger than or equals to. Okay, so that tells you if in this region, at every point in this region, the value of f is the same as the value at this x naught, y naught, that is still a relative maximum or minimum. So imagine that you have a plane. If you have a horizontal flat plane, then every point on this plane is a relative maximum or minimum because it has the same height everywhere. Okay, now we have the definition of relative extrema. The problem is if I give you a surface or a function and ask you to find the relative extrema, the definition doesn't really help you. You can't go from point to point and just keep and find all the values. It's not practical. So we have to devise a way to compute the local extrema. And here's how that rule is derived. So consider this point right here. Okay, in this case, our z is f of x and y. All right, and let's consider this relative maximum. If we consider only if we consider the trace f of x and y naught. So that means we fix the y coordinate, but we vary the x coordinate, and that gives you a trace or a curve, right? Now that curve on the graph, it will look something like this. So it's a curve that lies on this surface. Now, since this point is a relative maximum, then it means if we consider this curve, this point, the value of f at this point is still a maximum, right? So that tells you if you differentiate, not differentiate, that tells you since this point is a maximum on a curve, it tells you the slope at that point on this curve is horizontal. Is a maximum of the trace f of x, y naught then the slope of this trace at this point is 0. That comes from simple 1D calculus. If we have a function of one variable, then at either local minimum or maximum, we get 0 derivative or 0 slope. Okay, now remember from the last lecture, we learned that the slope of the trace at this point is the slope of f, the function f, oops, at this point x naught, y naught, in the x direction. Right, since f is a function of two variables, we cannot just talk about the slope, we need to give a direction to the slope. Now we're talking about the slope of this particular trace given by fixed y naught. Then the slope of this trace is the slope of the surface at this point in the x direction, which is equivalently, which is df dx, evaluated at x naught, y naught. Okay, and then use the same argument consider the trace of fixed x coordinate, so f of x naught, then y. Now we fix the x coordinate and vary the y coordinate. We get, follow through the same argument, we get df dy evaluated at x naught, y naught equals 0. Okay, now notice that this argument does not depend on this point being a maximum or minimum. So because it doesn't matter whether this point is maximum or minimum, the slope at this point will always be 0, because the only place we used the extrema property is to conclude that the slope of the trace is 0 at this point. Now if it's a minimum, the statement still holds. So that means we can expand this statement to maximum or minimum. Okay, so for all maximums, relative maximums, or relative minimums, we have the property f partial x equals 0 and f partial y equals 0, which gives us the first partials test. If, that is, if these are the simplified notation for the partial derivatives, if they exist, first of all, at the point x naught, y naught, That means the derivative. That means the derivative exists at this particular point, or the derivatives are defined at this particular point. Then, oh, here. And if x naught, y naught is, maybe I should write this. If they exist at this point, because two ifs is grammatically incorrect. If they exist at x naught and y naught, and x naught, y naught is a relative maximum or minimum, or you can write relative extremum, then f partial x evaluated at x naught, y naught equals 0, and f partial y evaluated at the same point x naught, y naught equals 0. Okay. Now we need this condition that the derivatives exist. Is the reason we need it is that if the derivative doesn't exist at some point, then that point, it doesn't mean that point is not a relative extremum. It still can be an extremum. So that's what you need to check when you use the first partial test, first partial derivative test. And you realize that the partial derivatives of f don't exist at some point. It doesn't mean that you shouldn't just exclude that point. You should actually take a look at that point and see what happens around it. So the partial derivatives not existent doesn't imply minimum, doesn't imply anything about this property. Okay, for example, so for example, that's actually what this critical point is all about. So let me introduce the definition of a critical point. X naught, y naught is a critical point if f partial x, x naught, y naught equals f partial y, x naught, y naught equals 0, or either f partial x or f partial y doesn't exist. Okay, so there are critical points that are not characterized by the partials being 0. There are some that are characterized by derivative non-existent. And that also can be a relative minimum or a maximum. So if fx, x naught, y naught equals Fy x naught y naught not equals if this equals 0 or Fy x naught y naught. What am I doing? If f partial x or f partial y doesn't exist, that's what I meant to write. It does not exist. X naught, y naught may still be a relative extremum. Okay, let me give an example here. Imagine that you have an axis, three-dimensional coordinate like this, and you have a pyramid on it. How do we draw a pyramid here? Say something like this. Okay, then look at this top. Now this point is still a relative maximum, obviously, but this is critical point. And also, it's a maximum. Now this point obviously is still a relative maximum, but you can tell that the derivative doesn't exist because it's a sharp angle. Whenever you have a sharp angle or a sharp corner, it means the derivative doesn't exist at that point because you're if you go to this point from this side or this side, you get two different velocities. That means the derivative doesn't exist. So the derivative not existing doesn't necessarily imply it's not a relative extremum. Okay, but for a majority of the equations you will encounter, the derivative should exist everywhere. There might be some cases where you have to consider these corners though. Okay, now remember that for the first partial test we say a point is a relative maximum or minimum, then f partial x and f partial y are both 0. Now is the counter argument, so this is the question. Is the converse of the first partial test true? I.e., does f partial x equals f partial y imply that the point x naught, y naught is a relative extremum. Mark. And the answer is no. Well, just like, I mean, if you've seen the term saddle point, uh, you should remember that in basic calculus, in the one-dimensional calculus, we've also encountered something called the saddle point before, right? And that's the one-dimensional analogy of what we have here. So the answer, of course, is no. Just like in one-dimensional, in the one-dimensional functions, you have saddle points. In two-dimensional functions, we also have saddle points. So the answer is no. It can also be now the saddle point is actually defined exactly this way. That is, the points that satisfy. So maybe I should erase this. So let me explain why the answer is no first. Well, the answer again is hidden in this graph. If you look at this point in the middle here, and again we consider the trace f, consider the trace fx naught y, then this is the trace. Okay. Now we see that this point is let me write this f x naught y. We see that this point is a maximum on this trace, and that implies f partial y at this point is 0 because it's the trace of fixed x naught as a function of y. So the partial y is 0 at this point. And if we look at the trace where y is fixed, we will get a curve that looks like this. And this is the trace f of x, y naught. And we notice that this point is a minimum on this trace f of x and y naught. And that again implies f partial x, f partial x is 0 at this point. So we see that even though it satisfies the conditions f partial x and f partial y are both 0, this is not a relative extremum, right? Because it's neither a minimum or a maximum. It's a maximum on this trace, but a minimum on this trace. So that means it's neither. Because in any neighborhood around it, you can find points that have smaller values than it and points that have larger values than it. So that's what we call a saddle point. So here the explanation is because the value of, let's just write, because the point x naught y naught can be a minimum on one trace and a maximum on the other trace. So that tells us the converse of the first partial test is not true. we can only if a point has 0 partial derivatives, we can only say it may be a relative maximum. We cannot say with certainty that it is indeed a relative maximum. It can be points of this nature. And these are the points that we call saddle point. X naught, Y naught is a saddle point if it satisfies the first partial test, which is f partial x at x naught, y naught equals f partial y, at x naught, y naught equals 0, but x naught, y naught is not a relative extremum. Okay, now let's use what we learned so far to do a couple practice problems. First example, find relative extremum of this function f of x and y equals 2x squared plus y squared plus 8x minus 6y plus 20. All right. All right. So the first step is if you want to apply the first partial rule, then the first step is to compute the partial derivatives. So the partial derivative with respect to x is 4x plus 8, and partial derivatives with respect to y is 2y minus 6. So immediately we notice that f sub x, f partial x, f partial y exist everywhere. That means there are no critical points characterized by partial derivatives not exist. Okay, so we only have to worry about the partial derivatives being 0. Now, apply the first partial test. We know that if, say, x naught, y naught is a maximum or minimum, then f partial x, f partial y have to both be 0. So we set the equation f partial x equals f partial y equals 0. That gives us 4x plus 8 equals 0, and 2y minus 6 equals 0. X equals minus 2, y equals 3. Therefore, 2 minus 2, 3 is the only critical point. Now, is this a relative extremum? To do that, we have to. There are two ways of doing it. First, we can graph it. So let me write this. Two methods to determine if this point minus 2, 3 is page here. Well, the first method is very straightforward, just to graph it. If you graph the surface, if you graph this surface, you will realize it looks something like this. This is the way to draw it, probably. Okay, and this point has the coordinate minus 2, 3, 3. That's just obtained by plugging in minus 2 and 3 into our expression for f. You will get 3 as an output. So it's like an upside cone, but with smooth corner. It's not a sharp corner, it's a smooth bottom. If you're not sure how to graph this, check, I believe it's lecture 4. Yeah, I think it's the last lecture. This is one of the 6 surfaces we talked about in the last lecture. Okay, so if you graph it, you will immediately see that this point is a relative minimum. The second method is to analyze the function directly. We have f of x and y equals 2x squared plus y squared plus 8x minus 6y plus 20. We need to complete the squares. So we get 2 times x squared plus 4x. Now we need a constant to make this a complete square. And that constant needs to be 4 because x squared plus 4x implies you need x plus 2 squared. Therefore, you need a constant 4 here. And similarly, y, the y term is y squared minus 6y, and the constant here needs to be 9. Okay, and now we have 2 times 4 plus 9, which is 17, but we had 20 before. Well, we had 20 to begin with. That means we have an extra 3 at the end. All right, turn this into squares. We have 2 times x plus 2 squared plus y minus 3 squared plus 3, and then it becomes obvious that 2 minus 3 is a relative maximum because f of x and y is larger than or equal to 3, which is f of minus 2 and 3 for all xy. This comes directly from non-negativity of squares. Since this is non-negative, this is non-negative, then you're adding something non-negative to 3. You can only make it larger. That means f is always larger than or equal to 3, which tells you minus 2, 3 is a relative minimum. Okay, let's do another one. Example 2. Let's find the relative extremum of f of x and y equals 1 minus x squared plus y squared to the 1/3. Alright, the first step is, again, compute the partial derivatives, f partial x equals minus 1/3 times x squared plus y squared to the 2/3 times 2x. And f partial y is the same thing except multiplied by 2y instead. Or this is minus 2/3, sorry, minus 2/3 and then times 2y. Okay. Well, we look at the partial derivatives. First, let's solve the system of f of x. Well, first, let's see if there are check for points where f partial x or f partial y doesn't exist. Well, since this is something to the minus 2/3, we can write this as 1 over x squared plus y squared to the 2/3. Right? And therefore we know that f partial x, f partial y does not exist only when x squared plus y squared to the 2/3 equals 0. That's the only restriction because it's a fraction, and the fraction doesn't exist when the denominator is 0. Now, x squared plus y squared to the 2/3 equals 0. That means x squared plus y squared equals 0. And that means x equals y equals 0. So, f partial x and f partial y does not exist. So we found our first critical point. Note that in this case, both of these partial derivatives do not exist at this point. But that's actually not necessary. All you need is one of them not exist. So if, say, f partial x doesn't exist, but f partial y does exist, that's still a critical point. So just keep in mind that that's what you're looking for. You look for one, as long as one partial derivative doesn't exist, then it's fine. Of course, the partial derivative that does exist has to be 0. Okay, so we found our first critical point. Now let's see if there are others. Well, so for all other critical points, the partial derivatives now do exist. then in order for them to be critical points, we have this equation: f partial x equals f partial y equals 0, which means, let me write this again, minus 1 over 3 times x squared plus y squared minus 2 over 3 times 2x equals 0. Times 2y equals 0. Okay, now a number with negative exponent is never 0 because it can be written as a 1 over something, and that's never 0. When you're dividing 1 by something, it doesn't matter how large the denominator is, the fraction never gives you 0. So that tells you this part will never be 0. Therefore, 2x and 2y have to both be 0, and you again get x equals 0, y equals 0. Now what does that tell you? It tells you that in order for f partial x and f partial y to be 0, x and y both have to be 0. But we just showed x and y, at this point the origin 0, 0, the partial derivatives don't exist. Right? So, but f partial x of 0, 0 and f partial y 0, 0 do not exist. Therefore, this has no solution. So we know 0, 0 is the only critical point. Okay. The last thing to do, of course, is to determine if this critical point is a relative extremum or not. Again, two methods. To determine if 0, 0 is a relative extremum. All right, the first method is once again graphing it. Well, this is not this equation. This f is not one of the 6 fundamental surfaces we talked about in the last lecture, but it's not too hard to graph. So if you look at the cross sections on the if you cut it horizontally, I mean, if you look at the trace on planes that are parallel to the xy plane, you'll realize that c equals 1 minus x squared plus y squared to the 1 over 3. And that means x squared plus y squared equals some constant, and that gives you a circle. So it tells you that the cross section on the cross section on planes parallel to the xy plane are circles. Now, when f gets larger than 1 minus f, when f becomes larger, or if you let z equals f of x and y, the height, or z, becomes larger, then 1 minus f becomes smaller, and that means the radius becomes smaller. So you get a shape with the horizontal traces being smaller and smaller circles, up until 1 point, which is this point we have 0, 0, 0, and at that point, you reach a maximum. So I'm just telling you it's a maximum. And if you graph it, since the partial derivatives do not exist at this point, it means it's not a smooth transition, but instead a sharp corner at the top. So it will look something like this. Not an excellent graph. It's not at all an excellent graph. I mean, if you don't understand my my graph, just type it into any graphing calculator and see it for yourself. All right, the second method is simpler because graphing this thing by hand is kind of difficult. One last. This is a mistake. The top is not the origin, but 0, 0, 1. Because note that f of 0, 0 is 1, so it's oops. Okay, yeah, it's even worse than the last one. Type it into an online graphing calculator and see for yourself. All right, the second method is to analyze the equation directly. Let me copy the equation here. F of x and y equals 1 minus x squared plus y squared to the 1 over 3. Well, since x squared plus y squared is non-negative for all xy, well, so is x squared plus y squared to the 1 over 3. Right? You take a positive number or non-negative number to the power of 1 over 3, you still get a non-negative number. And that tells you f of x and y is smaller than or equal to 1 for all xy. And since f 0, 0 equals 1, this is a relative maximum. Now, the method we've been using to determine relative extremum is quite tedious. We keep graphing everything to check if a point is a saddle point or a relative maximum or a relative minimum or maybe just a critical point. So mathematicians, to solve this problem, have devised another test called the second partial test. It gives you a simpler method to determine, to classify all the critical points. Okay, let me introduce what this second partial test is. First, let f have continuous second partial derivatives All right, let me underline this continuity assumption here. On an open region containing the point AB for which f partial x evaluated at AB equals f partial y evaluated at AB equals 0. Okay. Now to apply the second partial test, we do require the second partial derivatives to be continuous. But don't worry. Usually, most of the equations you see in this class, if they have a second partial derivative, it will be continuous. It's good practice to check it yourself every time, but usually that's the case. And continuous functions are most continuous functions that you encounter are pretty obvious. You don't have to prove that it's continuous. For example, f of x equals x. You just know it's continuous. So if you can find the second partial derivative, most likely it will be a continuous function. But do check just to be careful. Okay. In tests or exams, you don't have to write that down. But I just think it's good practice to confirm every component of the theorem. All right, let's consider the quantity D defined by fxx AB times f partial y AB minus f partial x partial y AB squared. Okay, this is the quantity we need to consider. Now, why is this? It's a little bit out of the scope of this course. It has something to do with the Jacobian. If you're interested, look it up on Google and try to read a little about it. But if this seems just out of nowhere to you, don't worry. Just memorize this. Just memorize this quantity. It happens quite often in calculus. Okay. Quantities of this form happens quite often in calculus. All right, so the first scenario, if D is larger than 0 and f partial x is larger than 0, then AB is a relative minimum. Second, if d larger than 0, and f partial x is smaller than 0, then AB is relative maximum. And third, if d is smaller than 0, then AB is a saddle point. Okay, so far we've considered d larger than 0 and d smaller than 0. So the last case is if d equals 0. Now if d equals 0 is the special case. D equals 0, it doesn't tell you that it's a relative maximum or saddle point or not. It means the test has failed. So if d equals 0, the test gives no information. So that means this test has failed. You have to either graph the function. You have to either graph the function yourself, or you have to, for example, go through the analysis that we just went through before, like consider the value of the function in a small neighborhood around it, consider the lower bound, upper bound of f, and that sort of thing. Okay, this is the second partial test. Now let's put that into practice. First practice problem. Classify all critical points of the function f of x and y equals xy minus x to the fourth divided by 4 minus y to the fourth divided by 4. Okay, first step, as always, compute the partial derivatives. F partial x equals x minus x cubed and f partial y equals, oh, sorry, I meant y minus x cubed f partial y equals x minus y cubed. Now immediately we see that f partial x and f partial y exist everywhere, so there are no critical points at which the partial derivatives don't exist. So we only have to consider the points where these partial derivatives are 0. Okay, now from the second or from the first equation, we know that y equals x cubed. Therefore, plug this into the second equation, we get x minus x to the 9th equals 0. Or equivalently, x times 1 minus x to the 8th equals 0. That tells you x is 0 or x equals plus minus 1, because x to the 8th equals 0 gives you two solutions, 1 and minus 1. All right, and the points, you just plug this back into our equation, we get 3 critical points. When x is 0, y equals 0 cubed, also 0. Start a new line. So 0, 0, the first critical point. When x is 1, 1 cubed is 1, so 1, 1. And minus 1 cubed is minus 1, so minus 1, minus 1. All right, we have these 3 critical points. Next, let's classify them. To apply the second partial test, of course, we need to first compute the second order partial derivatives. F partial x equals, so take the partial derivative with respect to x. On top of this, we get minus 3x squared. And then fyy equals minus 3y squared. And fxy is just 1. Okay, and from these we get our d, the quantity that we talked about before. The formula for this d is fxx. Let me just repeat that here just because it's important to memorize it. Minus fxy squared. Okay, so here we have minus 3x squared times minus 3y squared, that's 9x squared y squared, and then minus 1 squared, which is just 1. Okay, so consider the first point, 0, 0, then fxx, first d evaluated at 0, 0. We'll plug it in, you get minus 1. And that immediately tells you 0, 0 is a saddle point. All right, the second point, 1, 1, d11 is 8. So that means it's a relative extremum. Whether it's a maximum or minimum depends on the sign of fxx. So plug this point into fxx, we get minus 3. So that tells us 1, 1 is a relative maximum. And similarly, for the last point, minus 1, minus 1, plug this into d and fxx respectively. D of minus 1, again, equals 8. And fxx of minus 1 is minus 3. Therefore, minus 1 is also a relative max. Okay, for our last problem of the day, let's look at a real-world application of the partial derivative tests. Maybe not that real world. We're still talking about volumes and stuff, but it's an application problem. All right, so consider all rectangles all rectangle boxes, so three-dimensional objects that are resting on the xy plane. With one vertex at the origin and the opposite vertex on the plane (6x plus 4y plus 3z equals 24). And we ask, what is the largest possible volume? To visualize this, let's draw a three-dimensional Cartesian coordinate. So the shape looks something like this. Okay, and this point has the coordinate xyz, because this is the point opposite to the origin right there. The one edge of the rectangle overlapped with the y-axis a little bit, but you get the idea. This is the vertex that's opposite to the origin. All right, so if this point has coordinate xyz, then the volume, which denoted by v, equals xyz, right? Because the vertex opposite to xyz is 0, 0, 0. So the volume is obtained by x minus 0 times y minus 0 times z minus 0, which is xyz. And since this xyz lies on this plane, we can express z in terms of x and y, right? So this we have the plane equation for the plane, 6x plus 4y plus 3z equals 24. That tells you subtract both sides by 6x plus 4y and then divide it by 3. You get z equals 24 minus 6x minus 4y divided by 3. So replace z with this expression. We get the volume is xy times 24 minus 6x minus 4y over 3. It might be better to split this into 3 different fractions. 24 divided by 3 is 8, so 8xy. Six x divided by 3, 2x, so minus 2x squared y. And the last term is minus 4 over 3 xy squared. Alright, so we've successfully written v as a function of x and y. Now to get since we're finding the largest volume, we are finding the relative maximum. And to find the relative maximum, we apply the first partial test, and we compute v partial x and v partial y. Now v partial x equals 8y minus 4xy minus 4 over 3 y squared. And v partial y equals 8x minus 2x squared minus 8 over 3 xy. And they both equal 0. Now notice that in the first equation we have a common factor of y, and in the second equation we have a common factor of x. So let's take the common factors. We get y times 8 minus 4x minus 4 over 3y equals 0, and x times 8 minus 2x minus 8 over 3y equals 0. Okay, let's call this equation 1, call this equation 2. From equation 1, we know y equals 0, or 8 minus 4x minus 4 over 3y equals 0. From 2, x equals 0, or 8 minus 2x minus 8 over 3y equals 0. Okay, so you get four critical points. The first one is x equals 0, y equals 0. And the second one is y equals 0. Maybe I should write it the opposite order. Y equals 0, and 8 minus 2x minus 8 over 3y equals 0. So we're choosing this and this. Okay. The first critical point is this and this. Now this and that. And this, if you plug in y equals 0, you will get x equals 4. So x equals 4, y equals 0. Alright, the third point, you get 8 minus 4x minus 4 over 3y equals 0, and then x equals 0. Plug it in, you get x equals 0, y equals 6. The last one, 8 minus 4x minus 4 over 3y equals 0, and 8 minus 2x minus 8 over 3y equals 0. This requires a little bit of calculation. I'm not going to write all of that here, but the way you do it is you multiply the first equation by 2 and then subtract it by the second equation. So we get 16 minus 8x, and subtract the second one. Minus 8 plus 2x, the parts about y will cancel out, so you get 8 plus 6x equals 0, and x equals 4 over 3. And put that into the second equation or first equation, whichever you like. If you put it, for example, into the first one, you get 8 minus 16 over 3, which is 8 over 3, minus 4 over 3, y equals 0, so y equals 2. Okay, so we have our 4 critical points. Now apply the second partial test to determine whether they are maximum, minimum, or saddle points. All right, so we had f partial x and f partial y. We now v partial x, v partial y. We just need to compute the second order partial derivatives. V partial x is, I have to go back to the equation, sorry. V partial x is minus 4y. Seems quite simple, minus 4y. And v partial y equals v partial y equals minus 8 over 3x. And v partial x partial y is, if we differentiate the first one with respect to y, we get 8 minus 4x, then minus 8 over 3y. 8 minus 4x minus 8 over 3y. Right? Yeah. Okay, now the only thing remain is to plug each of these points into these equations. The first one, 0, 0. Yeah, 0, 0. Well, 0, 0, we know that f partial x, 0, 0 equals v partial y, 0, 0 equals 0. V partial x, partial y, 0, 0 equals 8. And therefore d of 0, 0 equals 0 times 0 minus 8 squared, so minus 64. So you get saddle point. This is not the maximum we're looking for. All right, the second one is 4, 0. Vxx 40, that's 0. Vyy 40 is minus 32 over 3. And Vxy 40 is minus 8. And once again, D40 is minus 64, which is also not what we want. All right, and the third one is 0, 6. Vxx 0, 6 is minus 24. Vyy is 0. Technically, we didn't have to do all of that. It's just that notice that Vxx depends on y entirely. Vyy depends on x entirely. So if one of these coordinates is 0, then Vxx times Vyy equals 0. So that makes D negative. But I'm just writing it out anyways. Vxy equals, plug this into Vxy, we get 8 minus 8 over 3 times 6, so that's minus 8. Once again, we get a saddle point. So we've had 3 saddle points so far. And the last one is, what's the number we have? 4 over 3 and 2. All right, Vxx, 4 over 3, 2 equals, it's minus 4y, so it's minus 8. And Vyy, 4 over 3, 2 is, plugging 4 over 3 and 2, we get minus 32 over 9. Oh, it's getting hard to calculate. Vxy is 8 minus 4 over 3 times 4, so 8 minus 16 over 3, which gives you 8 over 3, and then minus 16 over 3. So that's minus 8 over 3. And you get D equals this times that minus this thing squared. It's 256 divided by, well, sure, let's just calculate this. This multiplied by that is 256 divided by 9, then minus 64 over 9, which is 192 over 9, which is larger than 0. Now, since Vxx is smaller than 0, then this is a relative max. So we found our maximum. The only thing remaining is to actually compute the volume. Now the volume is max volume is, we'll plug in 4 over 3 and 2 into our expression for V. So it's just V of 4 over 3 and 2, and that would be It's a little hard to calculate in my head. But anyways, just plug in 4 over 3 and 2 into this equation, and that will be our maximum volume. Okay, that is all for today. The quiz has already been posted. Please finish it by the end of the please start it by the end of the day. So you have till end of the day. The quiz is due by the end of the day, and you can start any time during the day. But once you start, you have only 40 minutes to complete the quiz.